Hey, Math 7195. Here we are, unit number 12, Introduction to Statistical Process Control. Basically, we'll just be analyzing data over time, sort of in a quality control setting. This is just an introduction to this topic. It's basically an entire course or even a credential that can be earned in studying statistical process control. So we're just going to test the waters here. Basically, we're going to have data that's arranged over time, and we're studying something that's being, say, manufactured in large quantities. So we'll take some attribute or characteristic of the product that we're producing, and we'll measure that, and then we'll track its progress over time. Here's a little example of something called a run chart, where we're collecting data over time. On the x-axis, we have the observation, and then on the y-axis, it's the value of whatever we're measuring. So in this little example that I've sketched here, I was filling up 5-pound bags of concrete. So we're pouring the concrete into the bag, and then after it's in, we weigh them. So at the beginning, these are 5-pound bags of concrete, and we were doing really well. For many observations, everything seemed pretty good. Random fluctuation around 5 pounds. Then something seems to have happened around, the 54th observation. Things start to get a little more chaotic. The mean weight might still be 5 pounds. So that's one of the concerning things. If you were only keeping track of the mean weight of your bags of concrete, you might think that everything's fine and just continue on with your process, because even though you're having a lot of variability, you're erring above and below enough that on average your weight is probably pretty close to 5 pounds. But you can see very dramatically in this run chart that things have definitely changed here, and that would allow us to do some sort of investigation. When we're doing this sort of quality control stuff, it's not in this in this case, we're not really preventing anything. We're basically trying to detect problems and then try to fix them sooner rather than later. So this is a very simple plot that really can accomplish a lot. Just plotting data in the order that you get it or over time really can show a lot of information. Here's the same data that's plotted there. The way it was collected was I only looked at 5 bags per day. So on day 1, I weighed 5 bags. And then on day 2, I weighed 5 bags at 5 different times. And then day 3, 5 bags, and so on and so forth. So this data was 20 days, 5 bags per day. Maybe I measured at the same time each day, to get my first reading, my second reading, third reading, fourth, and fifth. We could study daily averages. Day 1, the average weight was 4.97. Everyone was happy. Day 2, average weight was 5.03. These are in pounds, and they're 5-pound bags. So if you're looking at the means, you'd see that, yeah, things seem to be going pretty good. You do notice that things are maybe, we had one day here, 5.2, and a couple more days where maybe we might start to think that something's out of whack here, maybe on the 18th or 19th day. But if we had plotted the raw values here, which we did above, we might detect that problem sooner, rather than waiting. If we were just looking at the means, we might not notice that there was a problem until here. But if we're looking at the actual values, we might detect it sooner. So sometimes when you pool your data together, you might miss something. We could also look at the range each day, and that might tell us something, right? A small range is good. That means our bags are being consistently filled. Uh, but if we have some large values, then we'll see that we're getting more inconsistent compared to how we were at the beginning. So that's another way to track this. And when we're doing this, usually these uh, methods are designed to be simple so that people working in the plant can monitor this and understand what they're doing. You don't need to be a statistician to understand means and ranges. So these and a plot over time, these things are nice, easy to understand, don't require a lot of training. So that's one of the reasons for them being like this. We're trying to find ways to detect problems in the simplest way possible. Things are determined or declared stable if we just have natural variation. We shouldn't have patterns or cycles. We shouldn't be systematically over or underestimating. Uh, those bags should just be getting filled. Uh, some are a little high, some are a little low, and no real pattern to it. With these problems, it's hard to uh, state rules for when it's stable or not stable, because it sort of depends on what you're doing. Like each specific situation uh, has its own special circumstances. So we have to come up with sort of general guidelines, and you tweak these things for the specific situation or product that's being manufactured. Random variation, good. Assignable variation, well, that's not good and maybe something that we can correct. So we try to identify, why are things not varying randomly? Here's Here are some common, you know, things to look for. You don't want your data trending up. We want random fluctuation. I just grabbed this screenshot from somewhere. So it's not relating back to our concrete data, 5 pound bags, but you can still get the idea. Um, Trending up means that something is, it's not running the way you expect it to. The bags are getting more and more full over time. Maybe the hopper that pours the cement into the bags is spring loaded, and over time that spring is wearing out. And then we could identify, oh, there's a problem with the spring. We need to maybe not use that sort of system because we tend to have this problem. Or maybe the hopper that's pouring the cement into the bags is starting to clog over time, and then the bags aren't getting as full. So these plots help you try to find out, uh, why are we having these sorts of behaviors? And I can't, we can't just come up with a a reason in a general course. It's really situation specific. But just running through some filling the cement bag example, suppose we're sort of underfilling and then suddenly we're overfilling, or maybe these aren't even, maybe both of these values are still close together. We're still close to 5 pounds for both, but why are we having a long streak of just under and then a long streak of just over? Maybe that has something to do with, lunchtime. Here's the morning crew, and then lunch happened, and then someone else took over. And we can identify that something changes. Maybe that we had different training for the morning shift than the afternoon shift, or the manager on one shift is different than the manager on another. Same with the downward shift, similar idea. We can also look for, really freakish values occasionally occurring. That's often identified by, maybe there was a mistake. Maybe we could find, an employee and retrain them so they stop making whatever that mistake is. Or maybe we'd notice that and go, well, maybe we need to give employees more breaks so that that doesn't happen. Or, things, it's all, it's all dependent on the situation, like I said. So we're just speculating here. Cyclical pattern in this plot. A lot of times this sort of thing appears when you have a human involved who has some control. So the the employee is monitoring the bags and notices that, oh, they seem to be a little bit full. Like they can see you know, the result of the bag after it was poured. And so they adjust the dial and then they overcorrect. And now the bags, they look in the bags and they go, oh, that doesn't look that full. So then they adjust again and then they're over and under. And you'll see these patterns happening where, yeah, I'm still maintaining my average, but maybe we shouldn't be doing so much correction. We should be finding a random pattern. So that's something that's kind of interesting. That's often a human, a behavioral reason for this sort of thing. And then there's the big one. This one, you see this a lot of times. You start out doing great, and then over time things just get worse and worse. You get more and more variation. Uh, that tends to happen just because things are, an example is parts are wearing out, and then uh, you're not doing as a consistent job as things are wearing down. So these are patterns that we look for in our run charts and other statistical plots. And again, these things are pretty easy for a lay person to watch out for. We looked at a run chart, and now we can make some other charts too. We'll call them control charts. These control charts will measure some characteristic like the mean or the range of the data. And the other thing that we'll add to those plots will be control limits. So we'll set boundaries for, basically what's expected and what is not expected. And whenever you go outside of that, limit, you know that you have a problem. Things are out of control, and now you should maybe evaluate and try to look for some sort of assignable reason for it going out of control. So we'll do two control charts, one for the ranges, it's called an R chart, and another one called an X bar chart. A range chart and an X bar chart. So we'll plot sample ranges over time, and we'll plot sample means over time. Some notation for us. N will be not the number of samples we have, but it's the size of each sample. Remember in our concrete example, we were checking each day over 20 days, and each day we checked 5 bags of concrete. So our N in that case is 5 samples, say, per day. And then we calculated the mean each day and the range each day. We could find the mean of those means. We'll call that X bar, which is also the mean of the whole group. The mean of all the means equals the mean of all of the individuals. And we'll also calculate R bar, which is just the mean of those sample ranges. So that'll get plotted in the center of the chart, or roughly the center, and then we'll come up with control limits for those, sort of like a confidence interval. So on an R chart, you'll have your ranges, getting plotted, and then we'll plot the mean of those ranges, and then we'll put limits. There'll be an upper limit and a lower limit, and then we'll we'll plot this, and hopefully we can make some deductions or figure out if the process is under control or not based on a plot like that. You'll see an example in a second. The uh, upper control limit and lower control limit. Again, we're trying to come up with the simplest way to determine these things. So it ends up being just the upper control limit is some factor times R bar. And the lower control limit is some factor times R bar, where these factors are just given in a chart. So an employee would just look in their chart and could use whatever value is given. These factors depend on the sample size. So, if you have small samples, you would allow for more variation, and if you have large samples, you'd allow these things would narrow down. So that's how those end up working from the chart. But basically they're very similar to they break down to roughly 3 standard deviations above and 3 standard deviations below, where we're trying to avoid using standard deviation because that's a more advanced statistical tool compared to something as simple as the range. So we'll make a control chart for the means as well. We had the mean of day 1, the mean of day 2, the mean of day 3, the mean of day 4, etc., and so on. And then the mean of the means would be X bar, and then we'll plot an upper control limit and a lower control limit, and we'll judge the data based off of that. And those control limits again are built similarly using a table. Instead of using a z-score and standard deviation for our limits, like this looks a lot like a confidence interval, X bar plus something and X bar minus something. This is your error estimate. Rather than defining it in terms of standard deviation and z-scores, it gets defined in terms of some factor from a table and R bar. And there's a reasonable relationship between, range and standard deviation. So that's how it's done. And here's your table of control chart constants. Those A's are in, this column. The D's from the R chart are in these columns. And there are other charts as well. So the table has a few extra columns for other ones. But for us, we're just going to focus on, basically these 3. And you just read these factors based on your sample size. In our example, we were filling 5-pound bags, and we were looking at 5 bags per day. So our constants that we use to find the control limits are given in the table here. Let's look at that example. So I used Excel to build this table. I had my daily totals. There's the mean of day 1. There's the range of day 1. To calculate X bar, I just had to find the mean of all these means. So add all those up, divide by n. X bar is your sum of your individual means divided by however many means you had. And in this case, that's the 5.069 pounds. And R bar is just the sum of your individual ranges divided by however many you have. And in this case, that's the 0.5250 right here. So I just added this column up and divided it by 20. To calculate your control limits for the mean, so X bar chart, upper control limit, go back and take a peek at the formula. It's x bar bar plus a2 r bar. So in our case, our x bar bar was 5.069 plus a2, which we read off of our table. So you go back to our control chart constants, and we're in this row, and we're using a2, so it's 0.577 as our factor there. And then multiply that by r bar. And doing that calculation, we get 5.37 pounds. And then you can do the lower control limit as x bar bar minus a2 r bar. You can see I just did it in Excel. I just made little formulas for these. So, but I thought I'd show it here. Again, the control constant is the same for this one. So we end up with 4.76. And we can do the same idea for our upper control limit for our R bar chart, or R chart. Go back and take a peek at the formula. I think these are on your big formula sheet somewhere. The formulas are pretty easy. It's D4 R bar and D3 R bar. So D4 R bar and lower control limit is D3 R bar. And now go back to your chart and find D4 and D3. D4 is 2.114 and D3 is 0. So 2.114 was our D4, and R bar is just staying the same. It's at 0.5250, and you get 1.1 pounds. And the other one was 0 times 0.5250, which is 0. And now we can look at these things on the plot. We just did the R chart. So here's the R chart for this sample. I plotted these ranges in order. So there they are, plotted over time. We had 20 different days of observations. On that same plot, I included the R bar. I think my color coding is all goofed up. If you look at that, R bar should be the center there. But obviously the R bar is here in the middle. Our upper control limit, we calculated it over here, it was 1.1, and our lower control limit was 0. And now we can see our data. Sometimes it's going outside the control limits, which is bad news. We can also see that there's a definite pattern there. Everything was going okay, and then all of a sudden things went crazy. So we can probably detect a problem with this plot. Our X bar chart, basically, again, I plotted my mean column over the 20 observations in order, and then I put the X bar in the center. Again, my labels didn't work out very well there. Not sure how that happened. Just the coloring. But anyway, here was our X bar of 5.06, and then we plotted our upper control limit of 5.37 and our lower control limit of 4.76. And you see that, again, things were going okay, but X bar was always higher than the projected value. Like, we want these bags to have 5 pounds. So that's a kind of a clear sign too. But it wasn't way above. But we can see by this pattern that something's gone wrong. Uh, I, I'm saying this, but I haven't given you any rules for how do we really evaluate these things. And there are basically 3 simple rules that are typically used. Uh, Rule 1 is if you see a pattern, trend, cycle, whatever, if it's not random, something's fishy. So that's the big one. Is there a point outside of the control limits? Even 1 point outside of the control limits can be a problem. So uh, those control limits are fairly conservatively set. So if you cross them, maybe it's time for investigation. Again, it depends on what you're manufacturing and how important it is to, keep the quality under control. Uh, in my bags of concrete example, it's probably not the end of the world if a bag gets shipped that's a little too full, or a bag gets shipped if it's not full enough. But in other circumstances, shipping a defective might be, really bad, and therefore we would have to have even stricter rules than what I'm giving here. One a basic run rule is a run of 8. This is to help you determine if there's a pattern or not. A lot of times these run charts, you're looking at so few points that it's hard to tell, if it's random or not. Because sometimes even in random data, you start to see streaks and things happen if you look at it on the short term. So one way to evaluate that is if you have 8 points in a row, all above or below that center line, that's likely a problem, that you're probably violating the, randomness, because we're expecting the values to basically alternate above and below. Sure, you can get a couple above and then a couple below and then alternate and then 4 above and 4 below, but it would be strange to get 8 in a row all above if there's a 50% chance that you're above or below. That's 0.5 to the 8th power, which is a pretty unlikely occurrence. So when you do see 8 in a row, that's a sort of a general guideline. But so we're going to use these rules. But again, it depends on your specific situation. Sometimes the rules get modified. Sometimes they use, other rules like 6 points going up or 6 points going down. That seems weird. Or 14 points alternating up down, because that would be a strange occurrence as well. And that's again, if somebody's at the controls and messing with they're adjusting it too much. And then, other things you can look for. We could go back and see how our plots are evaluated. Like back to the original run chart, here we have everything seems to be, you don't have, our center line is here. We don't have necessarily 8 points above or below at any given streak. It's hard to kind of tell here early on because it's so close to the line. But we definitely see that there's increasing variation. So there's definitely some sort of pattern or non-randomness happening there. With these other control charts, well, here we're violating all kinds of rules. There's certainly some sort of, non-randomness. We easily have 8 below and then a bunch above, and another one where we have 8 consecutive below. So that's a way to help software also identify problems. So, you can turn on a red light. You're monitoring these values, and whenever you have 8 in a row, flash a light or something to have somebody take a look at the plot. You can do another chart here, one for an attribute. Rather than measuring the weight, we can evaluate quality. So this is maybe a qualitative example versus a quantitative data. So you're looking for, you're evaluating something for, is it good enough? Is this defective or not defective? So we can monitor that percentage. So it's a percentage over time. So we'll call this a P chart. We're looking at proportions. And then the mean of a bunch of proportions is P bar. The pooled, you just pool all the data together and calculate the proportion of, say, defectives. And then Q is the opposite. Those are the proportion of things that are good. And again, we'll define N as the size of each sample, not the number of samples. It's easy to get those N's confused, maybe. When we go to make the chart, we'll plot a center line being P bar, and then we'll have upper and lower control limits. This time we don't need a control chart constant. We're going to basically use that. It's very much a binomial situation where basically 3 times the standard error, and 3 times the standard error will be the upper and lower limits. Because proportions vary between 0 and 1, sometimes these values end up outside of that range, and if that's the case, default them to 0 and 1, respectively. Quick little example here. We're going to put rivets into something. You put 10,000 rivets in an airplane or something, and we then inspect 200 of the rivets and evaluate them to see how, if they're properly seated or not. So we do that for 20 shipments. So say 20 different planes. And let's see if we're under control. So shipment number 1, we looked at 200 rivets, 5 were defective. So that day, the proportion of defectives was 0.025. And then, shipment number 2 had 3 defective rivets. And we just keep going. Shipment number 20 only had 1 defective, and we can calculate these proportions. Rather than calculating P bar by taking the mean of these guys, we'll just add up all the defectives and divide it by the total. So there were 4,000 total rivets. We did 20 shipments of 200 each. So there were 4,000 rivets that were inspected. P bar here is the 35 out of the 4,000 that we looked at. That's P bar. And then Q bar is 1 minus P bar. So this is the percentage of, okay rivets out of the 4,000. We determined our upper and lower control limits. Basically, the error is 3 times P bar Q bar over, is it N? Yeah. And then we put that error on P bar. So P bar plus error is the upper control limit, and P bar minus that error is the lower control limit. And they're calculated here. And the lower control limit ended up being negative. So just call it 0 because you can't have a negative proportion. And then we can make our plot where we'll plot these proportions. in the order that they were given. We'll have a center line of P bar, and we'll plot our upper and lower control limits as well. So here's what it looks like. Again, my key got a little messed up, but I think it's because I updated my version of Word. Like the document was made in Office 2012 or something, and then it got updated. It kind of messed with some of the formatting. That's what I'll blame this one on anyway. So you see the proportions over time. You'll see our P bar. It's the purple. We saw what it was here. It was 0.008. So that's this line through here, the purple line. And then I plotted the upper control limit, which was 0.02, 0.028. And the lower control limit, we had to set that to be 0. Now we have to look at this one, and it looks a little weird, but remember, you only have 20 values. So saying something is not random is pretty rough with such a small data set. We started out kind of high, and the values, did we have 8 in a row? 1, 2, 3, 4, 5, 6, 7, and then it dropped. So I guess by the rule of 8, we're still okay. Then we had 4 below, 1 above, 2 below, 1 above, 1 below, 2, 3 above. So we weren't having, streaks of above or below. I guess this is okay. Like I was a little worried there at the beginning, but basically, this is where we are right now in the process, and things seem to be okay. So, that was just a little blip in our data, maybe. So, or maybe there's something with the, maybe this was startup, and then maybe this process is affected by, some sort of, they get warmed up. The workers were getting a little bit better at their, placement of the rivets, but it wasn't enough to say it was out of control yet because there were only 7 in a row that were above. So I guess this one is okay, not out of control. Even though it is, a little bit weird, but not weird enough. We were touching the lower control limit, I guess, but it's impossible to go below. And I'm thinking here, if we're talking about defectives, 0 defectives is pretty good. So I'm not gonna, start saying shut down the process if I'm having no defects. I guess in this sort of plot, I'd be definitely more worried about flirting with the upper control limit, because that's the upper limit of defects that we would allow. And finally, in this topic, we can kind of put this into hypothesis testing context, where ideally you don't want to ship anything that's bad. And in this context, in acceptance sampling, I'm going to be talking about big shipments of large shipments of items. So basically, you break these large shipments into lots. Each 1,000 items is a lot, say. And you want to detect whether or not you should ship or not ship the lot as a manufacturer. Ideally, your lots are all perfect. And it's too expensive to check every item. So you only, you set up a plan where you sample from each lot, and then you come up with a criteria on whether you should reject that whole lot or ship it anyway. Say I have 1,000 item lot, I check 10 items, one of them out of 10 is bad, and I go, well, I can live with that, and you ship the whole lot. Or in that same situation, maybe I check 10 items out of the 1,000 and 3 are bad, and I can't live with that. So then what do? You have to go in and you probably don't just throw them all away. It depends on what the item is, I suppose. Sometimes you can just go and inspect them all, fix the ones that you identify as bad, and then you can finally ship the lot. But that's costly to you. So you have these things that are costly to you, and you have other things that are costly to the people that are buying the things. So uh, you don't really want either error, and the two tend to be linked. If you want to save your company money as the manufacturer by not rejecting bad lots, well, then the consequence is the people receiving the stuff end up with more defectives in what they're buying. So I mean, obviously, this is a huge topic on how you set up these uh, inspections. What size, how many items should I inspect out of 1,000? And then what should I set my tolerance to be? That's an acceptance number. Uh, the military has come up with a good quality control set of standards, and I think there are civilian ones that are used as well. Much of this stuff was developed, I think Japan was instrumental in the auto industry of kind of coming up with this whole idea of formalizing, you know, manufacturing and acceptance numbers and how to do the sampling process. But basically, you have a hypothesis test. Your null hypothesis is uh, the proportion of defectives is equal to the uh, the theoretical proportion of defectives that I would accept to be defective. As I'm shipping things out, I'm okay with 1% of my product having a problem. And hopefully that's what I'm manufacturing. That the stuff that I'm sending out has, and that actually is 1% defective. So that's my null hypothesis, is that 1% of my product is defective, and that's what I'm actually achieving. The alternative hypothesis is that it's higher in most cases. That's the bad case, if there are more defectives around than what you expect. So we can have terms like acceptable quality level, which is this P0, and we can have lot tolerance percent defective. And again, some of the mechanical students who took the engineering option, or who took the manufacturing option, they would have spent almost an entire course discussing this stuff. We're just getting a taste for it now that we're near the end of our course. We defined type 1 error and type 2 error uh, when we were first learning hypothesis testing. Type 1 error is when you reject the null hypothesis when it's true. Well, in this acceptance sampling, realm, that's called the producer's risk. If you reject a lot that is actually okay, that's costly to the producer, because then they went ahead and needlessly re-inspected all the items in the lot, or they threw the whole lot in the recycling bin. Uh, so that's why we call that the producer's risk. The consumer's risk is the alternative when you don't reject a lot that you should have. So when you took your little sample out of your 1,000 lot, and say in your little sample there were no defects, so you decided that the lot was fine and you shipped it. Where in reality, maybe every other item in the whole lot had it was defective, and that affects the consumer. So we define those terms just so that I want you guys to have this sort of, just have had a broad overview of this in case you're ever talking about these things with others. You at least have seen the language. Uh, what will I require of you, say on a test? Basically, I might give you a plot and ask you, do you think it's out of control? And you can evaluate it using the three main points we made about the pattern, 8 in a row, those rules. is how I would expect you to evaluate one of these plots. I guess I could ask you to make one, uh, but most likely I wouldn't. I think I'm more likely to give you the plot and ask you to evaluate it. And lastly, I guess I could also ask for some simple calculations. I could say, give you this plot without the control limits, and maybe I give you this other data, and then ask you to actually come up with the control limits so that you could have the opportunity to read that table of control chart constants. Uh, but basically, uh, being able to kind of look at these things and evaluate them, that's a reasonable thing to get out of this, and just have been exposed to some of this terminology of, say, accepted sampling. So yeah, I think that's it for this unit. I will see you all in the next one. Take care.